How many minutes? 5 minutes. Okay. Camera access. Hello, can start? Okay. Okay. Assalamualaikum and good afternoon to everyone. So today we're going to have a parallel session on Icfas Ps2 R2. So the first presenter, I would like to welcome the first presenter from Kazakhstan. So that is Associate Professor Gulzan Adukitowa. Okay, is it correct? Can you hear me? Can you hear me? Dr. Gulzan? Hello. So she will be our first presenter. So shall we continue? So the title today of paper is on the optimal control of the thermal exchange on a two-phase boundary layer. Okay, and you will present for about 10 minutes for today's presentation, and after that we will have a Q&A, question and answer, for about 5 minutes. Okay. Okay, doctor, can you hear me? Associate Professor Dr. Gulzan, are you ready? If you are ready, I would like to call you to proceed with your presentation, and now the floor is yours. Okay?
Good day, ladies and gentlemen. Today I would like to represent to you the topic of our article on the optimal control of the thermal exchange of two-phase boundary layer. This paper considers the problem of optimal control of injection into incompatible laminar boundary layer with boundary surface. Based on the necessary conditions for the extremum of auxiliary function, a system of equations is obtained for determining the Lagrange multipliers. A stream having the speed u of x, temperature T infinity, density ρ2, and viscosity μ2 outside the boundary layer flows around an asymptotically thin body from the surface of which a foreign liquid with a density of ρ1, viscosity v1, μ1 is supplied, which forms in the inner layer, which is represented in the figure 1. It assumed that the amount of injection fluid is small, so that the effect of injection only affects the fluid flow in the thin partial layer 1, does not introduce disturbances in a potential flow 2. We assume that there is a stable border between the media. In this case, the system of equations of a steady incompatible two-phase boundary layer in a rectangular coordinate system takes a form which is represented in the formulas from 1 till 5. The boundary conditions of the form are represented in the formula 6 and 7. and the conditions of boundary surface are represented in the formula 8 till 9, where sigma I are the Prandtl number of mu1 and Ki are coefficients of viscosity and thermal conductivity which depend on temperature. The following variation problems is posed among all unbasketable controls of VW of X determine one that would result in the minimum, which is represented in the formula 10. The amount of heat transferred from the hot gas stream to the plate of the given power of the cooling system are represented in the formula 11, where R of X is the thickness of the porous well. We believe that the given VW of X solution of the problem in the formula from 1 till 5 with the conditions from 6 till 9 exist and it's unique. Guided by the general approach to solving variation problems on a conditional extremum, we compose the functional, which is represented in the formula 12, where D1 is the area bounded by lines y equal to 0, x equal to L, y equal to y0 of x, and D2 is the area bounded by lines y equal to y0 of x, x equal to L, and y goes to infinity, and x equal to 0. It's all represented in a figure 2, and the parameters alpha and lambda I1 to lambda I6 are Lagrange multipliers. Consider the necessary conditions of extremum sigma I equal to 0. In expression 12, we leave only the control variation sigma VW, which is independent, and exclude the remaining variations. For this, we select the factors lambda ij, where I starts from 1 and 2, and j starts from 1 and 2 and goes to 6, so that they satisfy the system of equations, which is represented in the formula 13. Consider the contour integrals in expression alone. The lines x equal to 0, y equals to 0, x equal to L, and y goes to infinity. They satisfy the necessary conditions for the extremum. We found the boundary conditions for the solution of the formula 14. Variation of the derivative function y0 of x can be eliminated by the setting formula number 15. When integrating, we assume that sigma y0 of 0 is equal to 0, equating the coefficients of free variations to 0. In the formula 20, we obtain the conditions on the boundary surface. Now, the variation of functional number 12 is written as a formula number 17. Eliminating lambda I1 from the first two equations in system 13 and using formulas from 1 till 3, we obtain the equation for lambda I2, which admits the first integral, where lambda I3 is represented in the function fi from x and y, and phi I from x is some integration function determined from the boundary conditions. Consider the special case with mu I, which is constant, ki, which is constant, then the functional lambda I3 is found from the equation represented in the formula 19 with the boundary conditions represented in the formula 12 and the conditions of the boundary surface which is represented in the formula 21. Solving the boundary conditions of formula 14 and 16 relative to lambda I2, we find the formula number 22. On the boundary surface, we will have the formula number 23. The sequential descendant method allows us to approximately construct the optimal control First, we set the first approximately of control VW of x, by which we construct a solution to the system from 1 till 5, and then to equation number 23. Knowing the first approximation, u1, v1, and t1, and lambda 1, 2, we calculate the value of functions now represented in the article by formula 10 and 11. It should be expected that the control VW of x will be immediately satisfy the isoparametric conditions number 11 and deliver the minimum to the functional number 10. Therefore, it's necessary to change the control in the directions of the better correspondence. It's a conclusion. In the formulation and the solution of many problems of aerodynamics and hydrodynamics, an important role is played by the theory of boundary layer. This theory allows to characterize the ability of a transport object, ship and planes, to withstand and resistance of the gases and liquid medium during movement. The development of methods for controlling the boundary layer is associated with the goal of weakening and preventing flow, separating on the streamlined surface of the ship and the aircraft skin, reducing heat transfer and high flow rates. Thank you very much for your attention.
And next we will go on to the Q&A. Right. So anybody would like to ask questions? Yeah.
Hello.
Hello. Is there any question to ask for the presenter? Anyone? So we wait for the Q&A questions. Hello.
Okay.
We'll wait for a while. Any question? No question. 1 minute more. I think they're satisfied with the presentation. Okay. All right. Any question, guys? Anit, is there any question? Post in the presenter chat. I'm waiting. No question. So far, no question, Dr. Guzan. So, okay. All right. Thank you very much for your good presentations. All right. So we will move to the next presentation. So I would like to call the next one. The next one. Thank you very much, Dr. Guzan. So since there is no question asked, we need to proceed with our next presenter. So the next one will be the Nguyen Tian. Is it here? Nguyen Tian is from the Ps2 University, country Vietnam. So the title of her presentation is Some Inequalities for Sigma Convex Function. Hello.
Hello everyone. First of all, I would like to thank the organizer of the conference. My talk is some inequality for sigma convex function. A joint work with Ibrahim Mafri, UTP University. My talk is 4 parts. The first part I give some information. Second part the Karanata inequality, and third part the Ochoki inequality, and the last one is some common. The notion sigma convex function generalize the convex concept of geometric convexity, harmonic convexity, P convexity, log exponential convexity function. For each type of convex, consider various intervals in the inequality have been investigated. We focus on proving the parameter inequality and also key inequality for sigma convex functions. Now we define the notion sigma convex function. Let sigma be the strictly monotonic continuous function. A set I on R is said to be sigma convex if sigma inverse at 1 minus t sigma x plus t sigma y in I for any x and y in I t between 1 and 0. This notion generalized convex set notion. If we choose sigma the identity map, a function f from I into R is said to be sigma convex function if it satisfies the following inequality for any x and y in I and t in 0, 1. This notion also generalizes the notion convex function if for sigma e identity function. We have the Karamata inequality for sigma convex function. First, we define the sigma majorant notion. A type x1, x2, xn is sigma majorant with tuple y1, y2, yn if the following conditions are satisfied. First one is sigma 1, sigma is strictly with respect to xi and yi. It means sigma x1 bigger than sigma x2 bigger than sigma xn, sigma y1 bigger than sigma y2 bigger than sigma yn, and sum of all sigma xk bigger one sum sigma yk for any k run from 1 to I, for any I in from 1 to n minus 1 for any I in this set. And the last one is sigma k xk when k run from 1 to n equals sigma yk k run from 1 to n. Suppose the following theorem generalize parameter inequality for sigma convex function. Suppose that x I y I in I x y is sigma majorant of y I and f is sigma convex on I. Then we have sigma of fxi when I run from 1 to n bigger than summation of fyi when I run from 1 to n. The dilemma to prove Karamata inequality is the following lemma. Let f from I to R is sigma convex, then the different quotient fx minus fy over sigma x minus sigma y in non-decreasing with respect to sigma x if we fix y. Using this lemma, we can easy to prove Karamata inequality. third part of my talk is Ostrowski inequality. This theorem says that let f from I to R be an integrable function and sigma is a strictly monotonic function. If f is differentiable on integral of I and absolute value of f at t smaller than equal m for any t between a to b, then the following inequality holds. This inequality also generalizes standard Ostrowski inequality for sigma e identity function. If we define sigma convex function notion in easy way like this, last sigma from I to R is a strictly monotonic function. The function f from I to R equals sigma convex if the composition function f compose sigma inverse from sigma I to R is convex function on sigma I. Then if you define in this way, we can easy to prove Hermite's theorem like this. Suppose f from a interval a b to R is an integrable sigma convex function, then the following inequality holds. We can prove this theorem for several lines. Before this, my report, there are many results to prove Hermite's theorem, but it's quite all. Thank you very much for listening.
Now we will move on to the Q&A session. Okay, Q&A sessions. So let's open to the audience. Anyone who want to ask the question to the Tian, Dr. Tian, please send in the presenter chat. Hello, Dr. Nguyen Tian, are you there?
Yes, I'm here.
I cannot see your picture.
Sorry, because my camera has a problem, so I cannot turn on. I can turn on my camera, but I don't know why.
Okay. All right. So, there is no question, but let me ask a few questions to you.
Yes.
So, why do you want to do this research, Dr. Tian?
Okay, because I did a paper on a journal of inequality when about Hermite inequality for sigma convex function, but this theorem proved quite long. So when I visit UTP University, I meet Professor Paye. So I discussed with him, and we decide to prove the Hermite theorem in easy way and extend some result for sigma convex function like Kamata inequality and Ostrowski inequality for sigma convex.
Okay. All right. Thank you.
Okay, thank you.
All right. So, what is the significance of your research?
Okay, my research focus on M subunit functions that generalize pluri-subharmonic function and subharmonic function. And as a part, I'm studying about variation inequality.
So your contribution is something that new you introduce in your paper. What is the new knowledge that you propose?
Okay, I think since there are many because the new point there are many papers research on Ochoki inequality. For example, Dr. Pai and some his students. I think we can continue to research in this way for Ochoki inequality. I think because there several kinds of convex function, not only single convex function. For example, recently I read some about new notion of convexity, like I don't know exactly, but theta HM convexity. We can continue in this way.
Okay, all right.
Thank you.
Thank you, Doctor Yan Tian. Okay, that's all I think. Since there is no question from the audience, so next I would like to call upon our next presenter. Siapa ni? Imran Afroz. Hello, the next presenter. Okay, the next presenter is Miss Ernie, Dr. Miss Ernie. Is it correct? Hello, is it correct? What is the title? I don't have the name. Let me check. Okay. Okay, the title for her presentation today is the K-mean S clustering analysis. All right. So, Doctor, you are given 10 minutes to present your presentation, and then after that, 5 minutes will be the Q&A. Okay, now your floor is now. Okay, please start your presentation.
Hi everyone, I am Emisa Zainaiti. I am presenting my paper, K-mean clustering analysis for EEG features of situational interest detection in classroom learning. This paper proposed K-means clustering as a tool for situational interest detection. Previously, students' interests were evaluated using psychological measures. Questionnaires and self-report were commonly used. However, this kind of measures, known for being susceptible to subjective bias, and also it suffers from subjects pretending to engage. Here, physiological measures, for example, pupil diameter, electrocardiogram, and electroencephalography give an alternative. Physiological measures, especially EEG, assess the biomarker of subject's situational interest. Unlike the questionnaire, EEG signals cannot be manipulated, not cause interference to participants' attention, interest, or the session flow. We propose for develop a clustering method to automatically grouping the subject's situational interest based on their EEG features without relying on subjective measures. A brief introduction. Situational interest can be activated quickly. It has a simultaneous impact on students' learning, and it also effectively stimulated and estimated by physiological detectors. One way to measure situational interest in a classroom is by assessing the attention. Although there are literatures related to interest using EEG, however, in the scope of classroom learning, the literatures are limited. For example, Ko et al. 2017 proposed beta and theta power ratio to distinguish attentive and non-attentive students in a classroom. On the other hand, Palva 2007 proposed alpha frequency power to indicate the attentional level. We have three objectives in this project. Number one is to develop an instantaneous clustering method to detect situational interest. Number two, to determine EEG features of students' situational interest during classroom learning. And the third one is to measure correlation between physiological and psychological execution in assessing situational interest. In our project, there are 11 undergraduate students were participate in the experiment. Participant consists of 9 male students and 2 female students. One subject's data were excluded because of high artifacts. Students were attending 21 minutes of Laplace transform lecture presentation, with some interesting elements were included. The presentation questionnaire was undertaken once the experiment was done. Later, after being informed about the experiment flow, EEG was recorded using this protocol. After EEG signals was recorded, the signals were cleaned for the artifact and also the other noise. Later, EEG signals were segmented into 15 segments based on the subtopics length at the table 1 shown before. EEG features were extracted. Okay, power spectral density were being used because it is efficiently to characterize an individual activity. Figure 1 and figure 2 shows an example. Okay, you have a look here at the topo map, where the high or strong activated area, it will be indicated by a red color. On the other hand, the area which not activated or low activated will indicate by blue color. So from this figure, figure 1 it represent for low interested subject, where theta and alpha are more activated at the frontal area, while for high situational subject, beta and gamma were activated at the frontal area. The EEG features were calculated for each subfrequency, and it was served as an input to K-means clustering algorithm to cluster the students' situational interest level. Here, how the K-means clustering algorithm works, the objective function is to minimize the distance between set of point to the center of cluster. Here is the result. After K-means clustering was applied through all the frequency bands, it shows the best result only in alpha band. By using alpha inhibition hypothesis from 14 and 15, where they suggest that activation of neuronal processing region is increased by decreasing of alpha oscillation. So based on this figure, we can see that the students or the subjects that rely on the cluster 1 are associated with a high interest subject because it has a low alpha power activation, while students who belong to cluster 2 is associated with low interest subject, okay, because it is represented by high alpha oscillation. Those good biomarker to detect situational interest. So we compare the accuracy of k-means through different brain regions. So the accuracy was calculated on how effective the k-means algorithm distinguishes the two clusters in all subpoints of the presentation. Refer to table 2, frontal lobe shows highest accuracy with 93.33%, while frontal polar shows the lowest accuracy with only 53.33%. This result was supported by finding from Corsair, where the authors indicate that frontal cortex is mainly associated with attention and other important functions, including decision making, planning, working memory, language, and also judgment. Figure 4 shows that the summarization of k-means result in all subjects. Interested level represented by low mean alpha power, and non-interested level was indicated by high mean alpha power. So this preliminary result can be used as primary idea to develop an instantaneous automatic system to perceive the interest level of students while learning in classroom. This result also can be a real-time indicator for teachers and educators to have or to check the students' interest level during the learning session. We also compare the correlation between presentation score from the questionnaire and also k-means score from the clustering algorithm. Based on figure 5, there is a positive relationship between high score in presentation with a high k-means score, except for subject 3 and also subject 8. The presentation score will represent the situational interest score from the questionnaire. We use Spearman correlation test, and we found the correlation value is 0.388, with the p-value is larger than 0.05. So this result shows that there is a weak correlation with no significant difference between both parameters. This result may be because only 4 out of 15 subtopics were considered when calculating the presentation score. And lastly, for the conclusion, the ability of k-means clustering for situational interest identification has been determined. An instantaneous clustering method to detect situational interest without relying on psychological measures has been developed with 93.33% of accuracy. And alpha power at frontal region has been determined as EEG features of situational interest detection during classroom learning. And lastly, the correlation between psychological and physiological execution in assessing situational interest has been measured. That's all. Thank you from me.
Okay, thank you very much, Dr. Ernie. Dr. Ernie, correct? Okay, okay, thank you. So for your good presentation. So I would like to invite Q&A, question and answer from the audience. Anyone? Anyone from the audience wanted to ask the question? You can post in the presenter chat for me to read to the presenter. Anyone? No one here. Okay, if no one, so I would like to ask something.
Yeah.
Doctor, can you explain to me in a brief layman terms what is the meaning of your title of the thesis?
All right. Okay. What we want to propose is we we want to develop an automatic system to detect the interest of student during classroom learning. So
During?
during classroom,
Oh,
yeah.
yeah. Okay. So how do you
So
do it?
so we got the brain signal. So
Brain.
during
Yeah.
EEG,
Put
yeah,
on the head. Oh, ECG.
yeah,
Okay.
EEG, right? So our novelty is to because previously teachers detect the interest of student using
Mhm.
questionnaires, using survey.
Mhm.
So it lead to subjective bias.
Okay.
So what we propose is to develop an automatic system using the brain signal so that the outcome is not biased, okay? And it can be executed as a real time feedback.
Okay. Okay. Thank you. But it look a bit bulky, kan? Look on the top of the head. So how
Yeah.
do you suggest in future to make it more convenient for student to use that? And to apply in
Nowadays
the classroom.
the electrode is more commercial.
Mm-hmm.
It's just a look like a headband.
Oh,
No,
okay.
no strange
No
look
wire.
like, yeah,
Wire.
no wire
How
at
do
all,
you
wireless. So
use wireless
it
lah?
was
Wireless.
nice.
Okay.
Yeah.
So how does your model can be validated? How far is good compared to the traditional method of measuring this? What we call measuring apa? Interest kan? Detection.
Yeah.
How?
Uh, yeah. We have calculate the accuracy. So
Mm-hmm.
the 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 result shows it is excellent and it is promising. So we have about 93% of the accuracy compared to the previous traditional method.
Mm. Okay.
Yeah.
So 93% same lah, similar to.
Yeah.
Okay. Thank you very much. Okay,
Yeah. Well,
any others question from the audience? Tak ada. Tak ada. No more. Hello. No more question, doctor.
okay. Thank you.
Okay, thank you very much for your good presentation.
You're welcome.
One more. So, do you have intention to market your products?
Uh, we do not patent the hardware.
Yeah.
We propose the model to grouping the students based on their interest that is extracted by the brain signal.
Do
Yeah.
you have any intention?
Yes, of course.
Or how many percent already your model successful?
Uh, Currently, we're not approached to the patent yet.
Mm-hmm.
So, but we are working on a more large population
But
so
still
that
need to
yeah,
be research lah. Yeah.
yes,
They're going on lah from now time.
yes.
Okay. All right, doctor. So
Thank
thank
you.
you very much. Okay, since there is no question, and so thank you very much for your presentation today. Okay. So I would like to Anit. So I would like to call for the next presenter. That is Mr. Muhammad Naim. Mr. Muhammad Naim, Muhammad Arif. He is from UTP, University Technology Petronas, doing her PhD, okay, under supervision AP Associate Professor Dr. Anita. So his title is multivariate Gaussian process regression for evaluating electromagnetic profile in screening process of seabed logging application. Okay, and without further ado, I would like to call upon the presenter to present the slide now. Okay, welcome.
Hi everyone, my name is Muhammad Naim Muhammad Aris from University Technology Petronas Malaysia. Today's presentation is about multivariate Gaussian process regression for evaluating electromagnetic profile in screening process of seabed logging application. So this work proposed Gaussian process regression as the alternative forward modeling technique for screening process of SPL. So screening process is basically based on synthetic forward modeling codes to simulate EM responses. It can indicate limitation of the SPL towards the exploration regions. So computer simulation in the screening process can generate EM responses, but with high time consumption. Why? Because it involves very complicated mathematical equation and it needs time to solve numerous integral and the linear equation. So the idea of this study is to calibrate GPR and computer simulation in order to evaluate EM responses. So in this study, we use 3 independent variables and 1 dependent variables. Okay, so multivariate GPR model is capable of providing reliable information at all possible observations with low computation time and good accuracy. So this is the schematic representation of the SPL. So basically, there is HED transmitter towed by a ship and EM receivers located on the seafloor, and we have the potential reservoir underneath the seabed. So theoretically, GP is a collection of random variables such that any finite subset of the variable is normally distributed. Okay, GP is fully specified by a mean function and a covariant function. Why GP? Because GP is non-parametric and probabilistic method. It places prior on the function space without parameterizing the function. It also follows the Bayes inference by utilizing prior distribution to produce predictive distribution. So the objective of this study, the first one is to develop multivariate GPR model as the alternative technique for the screening process of the SPL. Second one, to validate the GPR model with the computer simulation outputs by computing the deviation. The third one, to compare the computational time taken by the GPR and computer simulation in generating the EM responses at all possible observations. So the first step is data acquisition. In this study, we use computer simulation technology software to generate the synthetic EM responses. Okay, this software utilizes finite element method to solve the solution. Okay. In this study, we have 2 different types of SPL models. The first one is target model. The second one is reference model. Target model is model with hydrocarbon layer. Reference model is model without hydrocarbon layer. So after we obtain all the EM responses, the normalized magnitude versus offset is computed between target and reference responses. Why? This is to detect the insignificant wave contribution in the EM responses. Okay, so these are the computer simulation inputs used in this study. The length, the width, the height are 20 km, 20 km, and 5 km respectively. Okay, the source length is 270 meter, and we use current 1250 ampere. 100 meter is used as the offset gap, and then we have 6 different hydrocarbon depths here, from 1000 meter to 2000 meter with 200 meter gap, and also we have 4 different frequencies. Okay, so each layer is parameterized with a very significant conductivity. Okay, so the next one, all the 24 EM datasets are tested at the GPR training set. These 24 EM datasets are generated using the CST software. So all these 24 EM datasets are treated as the GPR training set. Okay, so in this research, the training input is PQR. P represents the offset, Q represents the hydrocarbon depth, and R represents the frequency. So Y, as the training output, represents the magnitude of E field. So equation 2 is the prior distribution. So we use squared exponential as the covariant function as expressed in equation 3. So the idea of using a GPR model is to evaluate EM responses at testing input at unobserved input. So our unobserved input is denoted as Q star and R star. Q star is the unobserved hydrocarbon depth. R star is unobserved frequency. So Y star represents the magnitude of E field at the X star. Equation 4 is the posterior conditional distribution. Okay, so these are the basis of GPR model. We have predictive mean in equation 5 and predictive variance in equation 6. Predictive mean is the estimated magnitude of E field, which is the magnitude of E field at the X star. And the predictive variance is the variance along all the predictions made by the GPR model. So for the model validation, we use RMSE, root mean square error, and coefficient of variation, CV, between the computer simulation output and also the estimates made by the GPR model. So for the results and discussion, we concluded that only magnitudes of E field at offset of approximately 13 km to 19 km are considered for the GPR modeling. This is because of offsets of lesser than 13 km and greater than 90 km contribute to insignificant wave. Okay, so for results and discussion, these are the 24 EM responses generated through the computer simulation software. Okay, by utilizing these 24 EM responses, this 24 EM profile, we are able to generate 147 EM profiles by using the multivariate GPR model. So these 147 EM profiles are having different frequency, HC depth, hydrocarbon depth, and also different offset points. Okay, so in order to validate our GPR model, we compare the true value, which is the computer simulation output, and the estimate at the unobserved input, which is the untried HC depth and also untried frequencies. So based on the results here, we chose 3 different untried hydrocarbon depth and also 2 different untried frequencies. So the result from the results of the RMSE and CV are very significant. Okay, so computer simulation software required 18 minutes to generate 1 dataset with 1 hydrocarbon depth and 4 frequencies. So for 24 EM profiles, computer simulation software took 108 minutes for 6 depths with 4 frequencies each. So computer simulation could consume 378 minutes for 21 hydrocarbon depths with 4 frequency each, while GPR required lesser 5 minutes for 21 hydrocarbon depth with 7 frequencies each. When considering the computational time of the prior data acquisition, this study consumed lesser 113 minutes to produce EM profile at all the possible observation. Okay, solely utilizing the computer simulation could consume greater 378 minutes, more than 378 minutes for 21 hydrocarbon depths with 7 frequencies each. For the conclusion, EM responses for target model and reference model were successfully generated using the CSD software. The insignificant wave contribution was successfully identified by computing the normalized MVO, normalized magnitude versus offset. Multivariate GPR model was well developed. The average of the RMSE and the CV were lesser than 0.04 and 0.5% respectively. So the difference between the time taken by the computer simulation and the GPR to evaluate the EM profiles was very significant. So we can say that multivariate GPR can reduce the computational costs involved in the screening process of the SPL. So these are the references used in the conference paper. Thank you. My name is Mohammed.
Okay, thank you very much, Muhammad Naim, Mr. Muhammad Naim. So since he is not available, so Q&A cannot be proceed. So then we will move to the next presenter. So I would like to call upon our next presenter is Mr. Abdullah Muhammad Saad Said Al Yari. He is also the PhD student of UTP, and he will present today a topic on unsteady nanofluid flow over exponentially stretching sheet with vertical through flow. Okay, so without further ado, please present your presentation now. Okay, please proceed.
السلام عليكم ورحمة الله وبركاته. I'm Abdullah Liari. I'm from Yemen. I'm a doctoral student at UTB. My paper title is a study nanofluid flow of exponentially stretching sheet with vertical through flow. Background. A nanofluid is a single phase fluid in which nanoparticles are suspended. There are two effective models for convective heat transfer in nanofluid. The first one modeling was developed by Kuznetsov, and the second model was developed by Tiwari, which proposed model incorporating the effect of the nanoparticles by interaction on heat transfer enhancement. Many researchers have applied those two well-known nanofluid models. Work on through flow is significant because it allows for the monitoring of probable convective instability by modifying the through flow. Problem statement. Several researchers have used the Kuznetsov model to study the various flows and heat transfer problems in nanofluid. The model has one drawback, which is the active regulation of nanoparticles flux at the boundary, which is very difficult to implement realistically. We have corrected the Kuznetsov's prior work by including the convective term in the mass conservation equation, as it has been discovered that a convective term of the mass flux of nanoparticles should exist in the presence of the through flow. Research objectives. Number one, to develop a mathematical model for unstable flow, heat and mass transfer of nanofluid through an exponentially stretching surface based on a more realistic boundary condition of vertical through flow. Number two, to investigate the impact of vertical through flow and zero max flux boundary condition on flow parameters such as velocity, temperature, uh, and concentration profiles, as well as the skin friction coefficient and reduced Nusselt number. Methodology. The research methodology is briefly presented in the figure 1. Start geometry, MATLAB, solving, data analysis, and this study consists of heat transfer and flow studies. The simulation were conducted out in MATLAB utilizing the BB4C solver. In this work, the geometry considered is a plate as seen in figure 2. This is our geometry. It is a plate exponentially stretching plate. Okay, the governing equation for mass or continuity, momentum, and energy in an incompressible laminar single-phase flow are as follows. This is conservation of mass, conservation of momentum, conservation of energy, last one, concentration of nanoparticles. This is governing equations for this geometry. So from 1 to 4 can be written in Cartesian coordinate x, y, z, can be written in x, y, Cartesian coordinate x, y, z, using the boundary layer assumption. So you can we can write this governing equation in the Cartesian coordinate x, y, and z by using the boundary layer assumptions. From 6 until 9 are reduced to a system of non-linear ordinary differential equation using the similarity variables as follows. So we can convert the governing equation to a system of non-linear ordinary differential equation. So we can reduce it. We can reduce them from partial differential equation to ordinary differential equation, system of nonlinear ordinary differential equation. Now we can solve this system of nonlinear ordinary differential equation by using the B4C solver in MATLAB. The effects of various parameters on the skin friction coefficient, local Nusselt number, as well as the velocity, temperature, and concentration profiles are discussed. So from table 1, that an increase in Brownian motion parameter, okay, that's NB. It doesn't give any effect on the heat transfer rate for passive control. This is passive control. For passive control of nanoparticle, this is because of the implementation of the realistic boundary condition, which resulted in 0 nanoparticles flux at the boundary. Okay. From table 2, decreasing trend as is seen for the reduced Nusselt number as value of the thermophoresis parameter NT, this is NT thermophoresis, increase. Okay. Increase for both active and passive control of nanoparticles. As we see, this decrease and this decrease. This is due to thermophrasis accelerates the diffusion of nanoparticle and causes an increase in thermal boundary layer thickness. Okay. From table 3 shows the numerical result for the heat transfer rate without and with vertical vertical through flow taken into account. It can be seen that there is a difference of values of heat transfer rate between with and without vertical through flow. This is you can see the difference between values without and with vertical through flow. This is because when the vertical through flow is considered, the energy equation included the convective component. So that's why there is difference between without and with vertical through flow. Okay, from table 4, the increase of in thermophrasis parameter NT will decrease the local Nusselt number and an increase in thermal boundary layer thickness. Okay. From table 5 shows the Brownian motion parameter NB has no effect on the heat transfer rate, and so we can see the same value here, has no effect. Okay, and therefore negligible. This is because of the implementation of the realistic boundary condition, which resulted in 0 nanoparticle flux at the boundary. Okay. And from table 6, okay, when Prandtl number BR, increases, so we can see 5, 10, 15, the thermal boundary layer thickness decreases, which led to increase in the heat transfer rate. You can see here increase. This is due to decreasing fluid thermal conductivity as Prandtl number BR increase. So this why? Because decreasing fluid thermal conductivity. Okay. Table 7 shows that as schematic number SC increases from 1 to 5, the heat transfer rate decreases. So you can see here decreases. This is because higher schematic number SC will increase the momentum diffusivity, which resulted the widening of thermal boundary layer thickness and increase in temperature. Okay, so that's it, our result. Conclusion: the nanoparticle volume fraction at the boundary is passively controlled to get a more realistic result, and a convective term is added to the conservation equation of nanoparticle. The system of governing partial differential equation together with its boundary condition are reduced to nonlinear ordinary differential equation and then solve it numerically using BVP4C solver in MATLAB software. It was found that an increase in Brownian motion parameter doesn't give any effect on the heat transfer rate for passive control of nanoparticle, but decreases the heat transfer rate for active control of nanoparticle. It can also be seen that that increase in thermoflashes parameter NT decreases the local Nusselt number for both passive and active control. It was found as Brandt number increases, the heat transfer rate increases. Those are our references. Thank you so much. Assalamu alaikum.
All right. Thank you very much, Mr. Abdullah. How are
You
you?
are welcome. I'm
Yeah.
fine, thank you.
Okay. So you wait for the question. Question posed by the audience. So anyone to ask question to Mr. Abdullah can pose your question now. If no question, I start first. Abdullah.
Yes.
Abdullah, can you explain me your title? Your title, what you are doing now,
Yes.
where is your significance of the research? So why you want to do this study, and also what is the significance of your research? Okay.
The purpose of this research is to investigate and study flow,
Hello.
heat and mass transit. Yes, you hear me?
Yeah, I hear you. I hear you.
Yes.
Explain the
Can I
title
answer?
first. Title. Your title.
Yes. And study nanofluid flow over exponentially stretching sheet with particle through flow.
So what is the meaning of exponentially? Stretching.
Exponentially, that I mean very much stretching. Okay.
Why we use the term exponential?
Exponentially, that I mean with it more much stretching.
More stretching.
Yes.
Is it correct? The term you use? Hello? Hello? You please check. Is it the correct term to use for more stretching? By saying the exponentially stretching, yeah?
That's I mean wide range. I can wide range with stretching.
Okay. Proceed.
Yeah, that's it.
So what is your contribution?
Contribution of this work
Yeah. What is new?
is is investigate and study fluid heat and mass transfer of nanofluid over exponentially stretching sheet. Okay, this research this is model managed to nanoparticles passively at the boundary rather than actively, making it physically more realistic.
Your significance. Something I want to know. What is new? What is new that people haven't done yet?
Yes. With this work, we insert the term to conservation of mass, so we can correct this this drawback with insert convector to the conservation of mass equation.
Okay. All right. So any others question? I'm waiting. Any question from the audience? Okay, if no question, let's go through your problem statement. Can you turn on your problem statement? Who control? Abdullah,
Yes.
I want to see your problem statement.
Okay. Okay.
Okay, just show me.
You want me to
Yeah, open.
PowerPoint?
Yeah, open your PowerPoint.
Assalamu alaikum.
And let me see. So I just want to just comment on the problem statement.
Okay, wait. Doctoral student attitude.
Okay. Again, more further. Okay, here. Abdullah. So
Yes.
I think
Yes.
number one is not the look like a problem. Several research
Yes.
used testnet shock model to study the various flow and heat transfer problem in nanofluid. So is that the
Yes.
problem? Problem is something.
No.
Yeah, you
Yeah,
want
and this model has no drawback, which is the active regulation of nanoflex at the boundary, which is very difficult to implement realistically.
you have to
So
put
here,
the
so
right
here we,
problem. Okay, the right
so
problem.
we
You have to say here number one.
yeah, our problem from this model. So this model
Yeah.
has one drawback, which is the effective regulation of nanoparticles flex at the boundary, which is very difficult to implement realistically.
Yeah, you have to write properly.
So we have corrected this model by add this conflicted term.
Yeah, you have to write properly the problem number one. Okay. Yeah, Abdullah.
Yes, yes,
And also number three you cannot say you have corrected.
yes. We have corrected and add this.
But there is not a problem. There is not a problem. Okay. Correction is not a problem. Correction is a solution.
In the presence of the flow. Because this is research objectives.
Yeah. Just my suggestion. Okay.
Yes.
So you need to do some correction. So correction
Okay.
of the Casino works prayer work. You have to rewrite again lah. Not to say that you correct the model by Cornish walk, and that is your problem. That one is your solution. So you need to rewrite again to show that it look like a proper problem. Proper
Okay.
problem. Okay. The number two. Let's see your model. The model. Here. Here. Previous. Back. This one. Okay. Just. Okay. Is there any you should include geometry? What is the geometry that you want to?
Our geometry flat plate. Flat plate.
Blood blade.
Yes, flat plate. Yes.
Just put right down the word there lah. The correct wording lah. Geometry, I think to general. Okay, to general, what is the geometry, isn't it? So you have to be more specific. Okay. I think then
yes,
MATLAB. What are you doing MATLAB there?
Yes. I use MATLAB. Okay.
Is it needed? Huh? Is it crucial to put MATLAB? I think
Yes,
MATLAB is the program, isn't it?
yes,
You
you
always,
use MATLAB, yes.
yeah, I know. But how do you solve it?
Okay,
Huh? So
by
you have to write down properly your methodology. Okay, number one, what is the you want to go to do? Number two, number three, number four, like that. Not
okay,
saying that the method geometry is too what we call too general. Okay, so people are doing that.
yes,
Normally, all
yes,
people. So please
okay,
differentiate between these. Okay, because you are doing
okay,
your business.
okay,
Okay, eh? Okay, that's
okay.
all. I think. Just
Thank you so much.
okay. Thank you very much, Abdullah.
Yeah, thank you.
Next time, I hope you will improve and you get your PhD. Okay.
Okay, thank you, sir.
Okay. Thank you a lot, Abdullah.
Welcome.
Yeah. Anip. So I think by that we already come to the end of our sessions. So that's all I think. Anip. Hello.